Okay, good. So we get started with our webinar. I'm very happy to have Karen Keppler here with us today. Karen does not only have a lot of experience doing mid-infrared, high-resolution mid-infrared spectroscopy, which she got first, I think, in Gießen, and then later at ETH Zurich, where she worked in Martin Quackt's and Frederick Merkt's lab. But she also did a really great job analyzing some data that came out of a joint measurement campaign between the folks at ETH Zurich and us at IRsweep, where we were developing this combined high spectral and high temporal resolution mode of QCL Dualcomb Spectroscopy, and we did a study of atmospherically relevant molecules in supersonic beams using QCL Dualcomb Spectrometer. And I'm very happy that you are going to present those results. Before I give the word to Karen, I would like to give a short introduction to the technique that we use. And even before that, I would like to do two announcements. One is you may have seen a mail newsletter from IRsweep just before Christmas. We have released the laser module C. The laser module C is kind of a drop-in replacement for the existing laser module, the laser module A. So as the LMA, it contains two matching quantum cascade laser frequency combs in a module which are pre-aligned for Dualcomb spectroscopy, and it's compatible with all the existing IRIS spectrometers. Now, the main novelties of it stand in the C of it. C, like compact, it's hard to get from that picture here, but in fact, this module is only 12 by 12 centimeters in footprint, so it nicely fits into the palm of my hand, and therefore it also uses much less space in your lab. And maybe even more important for all of you is C, like cost efficient. We were able to get the prices of those laser modules down by more than a factor of 2, such that it's now wavelength dependent, but some wavelengths are available for as low as 25,000 euros. So if you would like to expand your wavelength coverage of Dualcomb spectroscopy, please get in touch whether the laser module C is suitable for you. A second announcement that is kind of a technical one, but I'm going through it quickly. We have released, or we're about to release, a new faster signal processing software. The problem that we're facing in QCL Dualcomb spectroscopy is shown here. We have data rates of 8 gigabytes per second coming out of our digitizer, and we somehow have to turn those into spectra. And you can imagine there's a lot of number crunching involved. There's a few steps we don't really have to care about, but where the main issue was the actual evaluation of the data, where we used to have a data throughput of 0.7% so far. So that means if you took a 10 millisecond measurement, it took you 1.5 seconds until you actually got the result out of this. Now, our software team did a great job over the past year to get this number up, and we are now ready to release this new software with a data throughput of 16%. So now, if you start with a 10 millisecond measurement, after only 60 milliseconds, you will have your data. And this is important for everyone who has to do many measurements in a short time. For example, if you do standoff detection and you want to look at many positions on a standoff distance, this is useful. Or in high throughput applications, if you imagine you have a conveyor belt which sends you sample after sample, and you have to see the spectra of all of those, then this new data throughput is needed. Also for imaging applications where you do pixel by pixel imaging and you have to evaluate all this data, this is now much faster. And finally, and that also gets us to the topic of our talk today, also in high resolution spectroscopy, we do something that we call step sweeping, which means we have to do many measurements to get a complete high resolution spectrum. And this process just got much faster. So now we're ready to get started with the actual method used here. here a brief explanation of Dualcomb spectroscopy. We have two frequency combs. The two frequency combs have slightly different mode spacing, and when you superimpose them, you have the situation as shown here, where each pair of modes has slightly different spacing and therefore beats at a slightly different radio frequency. Now, this is generic for all Dualcomb spectroscopy measurements. When we look at quantum cascade laser Dualcomb spectroscopy, then we have those numbers. We have a comb mode spacing of 0.3 wave numbers of our QCL frequency combs. We have more than 200 lines emitted by each frequency comb, which result in a coverage of more than 60 wave numbers somewhere in the mid-infrared. When we look at the acquisition side of things, then we have all those 200 beat nodes in the range of 0 to 1000 megahertz, which means we have somewhere between 1 and 5 megahertz spacing between those beat nodes in the radio frequency. Why is this important? Because the inverse of the spacing actually gives us the time resolution of our measurement. And from the 1 to 5 megahertz, you can take it that we can measure faster than 1 microsecond. We can measure the spectra faster than 1 microsecond. So take-home messages of this slide: more than 60 wave numbers coverage in less than 1 microsecond. And that's what this actually looks like in a measurement. What you see here is a combustion reaction. You see at time 0, we have a broadband absorber coming in, that is propane in this case. And then you can see how the concentration of propane decays. That's because it's very hot around there and there's pyrolysis happening. And then suddenly we have narrow band absorbers appearing. That is where the actual combustion happens, and water is being produced in that process, and we see the absorption lines of water. Now, why I'm showing you this is because it nicely illustrates the broadband measurement, which allows us to see broadband absorbers as well as many lines of narrowband absorbers. And it shows you the high time resolution. This complete process happens in 1.5 milliseconds, and the microsecond time resolution helps us to actually follow the dynamics of this process. What this image also shows you, however, is the shortcoming of this measurement. It's a bit hard to see in the 3D view, but if we look at a cut along the wavelength axis, then we can see that those narrowband absorptions are actually not very well resolved. So basically here you see this is one of those absorption lines, and we only have one measurement point on top of this absorption line. And that, of course, also comes from the parameters that I've shown you before. It's this 0.3 wave number spacing between comb modes. Probably many of you know small molecule gas-based absorption lines are narrower than 0.3 wave numbers, so we will undersample the spectrum. What we would like to have, of course, in high-resolution spectroscopy is a well-resolved line like shown here. This is now methane absorption line at very low pressure, so no pressure broadening, only Doppler broadening. We're looking at a line width of a few times 10 to the -3 wave numbers. And now, as you can see, suddenly this is very nicely resolved, and we see the Gaussian shape of this line. But this is also a QCL Dualcomb spectroscopy measurement. So how do we do that? What we do is we do interleaving of our spectra. So basically, we have to move our frequency comb over a range of 0.3 wave numbers. And once we've done that, we have filled the gap between adjacent comb modes and then get a high resolution spectrum over the complete coverage of the frequency comb. And we have developed together with Muriel Lepere from the University of Namur what we call the step sweep mode. In step sweep mode, we basically do this sweeping through the wavelengths in a stepwise fashion. So in the first step, we only move one of our lasers, which means we increase the spacing between beating comb modes, which means we will also move all of our radio frequency. why is this great? Because now we can accurately measure the step size that we did in the optical domain directly from our radio frequency spectrum. So we get a very accurate measure of the step that we did in the spectrum. Then in the second step, we move the second laser and we close the gap between the beating comb modes again and get the radio frequencies back to their initial position. And then we move the first laser again, and then the second, and the first, and the second, and so on, until we have moved through those 0.3 wave number spacing and get a complete high resolution spectrum. And here, this is what this really looks like. If we do that, again, you see a measurement of low pressure methane. You can see we observe the complete Q branch and parts of the P and R branches of the Nu3 band of methane here. You see from looking from afar, those absorption lines look kind of needle-like, but if we zoom in on one of those absorption lines, we can see that this is actually a well-resolved Gaussian line, which is measured with very, very high resolution here. Little side note, in Dualcomb spectroscopy, typically we do not only measure the absorption, but we also measure the dispersion of the sample. So at the same time, we also get this dispersion spectrum where we can see this dispersion feature for each of the transitions. An important thing to note for QCL Dualcomb spectroscopy is while we get a very accurate relative wave number axis from the step sweep measurement, we do not get any information or we do not have at first any information about the absolute frequency of our frequency comb. So what we typically have to do is a calibration measurement. So for example, as done here, this is now an N2O measurement. We use one of the transitions as a frequency ruler. So we say we know your frequency accurately, and then we can look at all the other transitions that we observe, how accurately we have measured their position. And what we found in such a measurement is that we get a frequency axis accuracy of ±4 megahertz, or roughly 1 × 10⁻⁴ wave numbers. This is now if you do the calibration in the same measurement as you do your sample measurement. If you oftentimes you will do first a calibration measurement and then later on a sample measurement. And we have also accurately characterized this process, and details are described in that paper with Muriel Lepere from University Namur. But what we have found there is that over a course of 24 hours, we have less than 12 megahertz or 5 × 10⁻⁴ wave number inaccuracy in our wave number axis. So that is about the spectral accuracy you can expect from those measurements. Okay, so far what I've shown you is we can do very highly resolved measurements of static samples, and we can also do high time resolution measurements with not a very high spectral resolution. Now, the beauty of this step sweep process is that actually in each position, your comb is standing completely still. So basically, we can just do this high time resolution measurement at each position of our step sweep. And if we do that, we combine the two techniques, what we get is a very high spectral and high temporal resolution at the same time. So we can now see those 10⁻³ wave number wide features, and we can observe their dynamics on a microsecond time scale. In conclusion, this gives us sub-microsecond time resolution with 5 × 10⁻⁴ wave number spectral resolution over a coverage of 60 wave numbers. And I think this is very useful for everyone who cares for small gas phase molecules and dynamics and their fast dynamics, for example, in plasma diagnostics, in combustion analysis, or also for high resolution measurements in cold molecular jets. And this is exactly what Karen Keppler is going to present us here. So I'd like to give the word to you, Karen, to show us how this was implemented at ETH Zurich and what you got out of those measurements. Karen, I think you're muted.
It's good now. Thank you, Markus. Okay, can you see my screen?
Yes.
Very good. Okay, first of all, before we get started, Markus, thank you for the very nice introduction. And thank you for the invitation to come and talk a bit about the research. Thank you. Now, what I'll be describing today briefly is some work that we did in cooperation with IRsweep at ETH. And what we've done is we've chosen two very interesting molecules because they're of atmospheric importance. And I'll be describing the work that we've done with that. To give you a little bit of an overview, this was a nice group of people that we put together, big group of people. You see that from ETH on the left and on IRsweep on the right, we had a good collection of people with a lot of different skills. Two molecules that we've studied were bad molecules. We studied CHCl2F, which is 148 times as bad as CO2 when it comes to global warming. And then we studied the super bad CF4, which is over 6,000 times as bad as CO2 when we're describing global warming. And so what we'll be talking about today is how we took the QCL Dualcomb spectra and analyzed this to get out some improved parameters for the molecules, and more than anything, to get a bit of experience with the new instrument. Now, I won't spend too much time on this because Markus has already discussed things very well. I would just like to do sort of a "you are here" sort of thing to let you know where we measured. I've said that we've measured two molecules. The CHCl2F was measured in combination with N2O. This was rather a weak signal, so we measured this without skimmer. CF4 was strong enough that we could measure it using the skimmer, and this made it possible for us to collect very low temperature spectra. And this led, of course, to a very nice and low effective Doppler width and helped us see a lot. To give you an idea of how this translates into real life, I'd like to draw your attention to the left of the screen. The jet that you saw would be running up this way. The measurements that were conducted would be in this plane. If you look to the right of your screen here, you see a close-up featuring the laser alignment, and that would be here on the setup as you see it. I'd also like to point out that if you have more questions about the details of what we did, every time we've got the figures in, I put in the reference to the paper. And so you can see the paper, which is available open source, if you've got questions on what we did or why. To give you a brief overview of what we looked at Nu3 and CF4. And now this band has been measured before. What we've done is tried to point out for you how it looks at the beginning and the end of our time-resolved measurement. We've performed a simulation which you can compare with the experimental measurement. And we've done the simulation using the parameters from HYTRAN. To give you an idea of how this looks when you do a close-up on it, let's look at the area right around the Q branch. You can see over here on the left, the P1 absorption, and you can see that we've got a fairly good reproduction of what we measured with our simulation. To look at some things in a bit more detail, let's look at some of the lower J transitions. Now here, the blue mark you see is a calibration that we performed to other CF4 measurements which had been performed in the laboratory. And our measurements, I would point out at this point, predate some of the calibration advances that Markus has discussed, because these measurements were taken about 2 years ago. And so it was very exciting being part of this as it was growing up. So you can see that what we've done, though, is made certain that we've got a good calibration, and you can see also that our line width is very good to work with. To give you an idea of what things look like during the gas pulse, we took a closer look at 4 transitions in CF4. And just to orient you very quickly, we see the decadic absorption or absorbance here on the y-axis. And what you see here are 4 transitions which we picked out and looked at in detail over the course of time. Now, assuming a Boltzmann distribution in the ground state, this helped us to determine the temperature as a function of time as being around about 30 Kelvin. Now, this, of course, was done with CF4, and we had the advantage of having the skimmer, so we were only looking at the very low temperature part of it. Now, this wasn't so true for the N2O and the CHCl2 measurement, but still, we could really get some good clean lines out, obviously, from N2O. And so we could look at these over time. And here we came up with a temperature during our measurement of about 130 Kelvin. So this helped us also to simulate what we were observing. To give you an idea and a bit of a perspective on how nice these spectra are, we've done a lot of previous FTIR measurements with this molecule in Zurich. And what you see here on your left are some original measurements performed by Marcel Snels using the Bowman. On the right, you see more recent measurements with the Brooker, which are also, we're looking at a very good line width here with fairly high resolution. But please remember that we're doing this by co-adding hundreds of scans, and each of those scans takes a fair amount of time to measure. And so it's pretty cool that we can take a desktop device and get the resolutions out which are being obtained. Now here you see the spectrum which we've taken for this study, and this is the QCL Dualcomb Spectrum. We're looking again at the CH bending mode in this molecule. And what's really interesting is if you look carefully, you see the Q branches not only from the Cl2 double 35 isotopologue, but also from the singly substituted. And you see also here on the right, you see an N2O trace, which provides a calibration. Now this gives you a little bit closer look at the aforementioned N2O lines and gives you a good idea of the line widths which we were able to obtain. And here you see the observed line widths which we had for some of the transitions CHCl to F. And again, you're seeing that we're working at very good line widths, and again, these things were measured quite quickly. We take all of these thousands of transitions and we break them down into something that's a little bit more manageable using something called a Loomis Wood diagram. And what you see here, of course, let me give you a little bit of orientation. Here you have a typical absorbance versus wave number diagram. And what we do is we take this and we slice it up, and then we put the slices on top of each other, actually under each other. And what you see from the top to the bottom of your screen is increasing wave number. In other words, the P branch is here on the top of your diagram, and you'll see that over here. The R branch is here, and you see that here. And what I can also point out is that these spectra were very clean. And so we were able to see not only the main isotopologue, but also the singly substituted. And so this made it pretty easy actually to go forward and to analyze the spectra. And so you can see here part of the P branch and what we were able to assign. And I would point out here that some of the assignments, of course, in the higher temperature regions were performed with the help of the older spectra that we had. If you look here on the 2 upper traces, you see components of the P branch from the singly substituted isotopologue. And if you look here at the lower 2 traces, you see the main isotopologue. Where I really was very, very impressed with the spectrometer is when I got a look at the Q branch in the spectra, because to have this clear of spectra to work with it's almost like cheating. It's very easy. Anyway, what we see here is just an enlargement of this part of the Q branch. You see this up here in the middle on the left. And if we go a little bit closer, we see that we can go ahead and analyze the Q branch pretty well. And so this is something that isn't always so easy. And so it's a good spectrometer that we can do that with it. To give you an idea of where we went further after having all these assignments, is we used Watson's S-reduced effective Hamiltonian to obtain new molecular parameters for these gases. And just to give you an idea of where all of this is going, here, of course, are your quartic distortion constants. Here are the sextic. And this just gives you an idea of what we found. And as far as a table of the results, I would refer you to the papers for that. Our most recent one has come out at the end of last year in molecular physics, and the reference for that is also at the end. To give you just an overview of what we've done, we've taken a high resolution spectrum of these two molecules, and we've been able to measure it quite effectively with a very low effective Doppler width. What we've done is we've gotten down to about 15 megahertz for CF4, where we're really not limited by the spectroscopy here. We're limited more by the fact that we, in our gas sample, don't have just one temperature. We found out that we agree pretty well with Hytran to within better than 30 megahertz. We have gone ahead and determined and published improved molecular parameters for these. And we've, as we've looked at CF4, it was quite interesting that we could find the temperature was pretty low to start and came up a bit to about 25. We had a temporal resolution as we looked at the time traces of about 4 microseconds. So what we've done in the end is we've taken a very new tool together with these older measurement methods, and we've combined it to really contribute to some advances in very high resolution spectroscopy and time resolved spectra as well. I'd like to thank all of the people who worked on this project, particularly Martin Quack and his research group, Frederick Merkt and his research group, and the other members of the team at the ETH and student Leon Beck who helped with the programming. We thank IRsweep and you, Markus, for inviting us. We'd like to thank everyone you see on the bottom of the screen there who supported our research. And I thank all of you for having come to listen to us today. Thank you.
Thanks, Karen, for this very nice presentation. To everyone, please use the Q&A feature to send some questions. We already got one more of a comment than a question from Julia Lehmann. She says, beautiful spectra and Loomis Wood diagram. I have to totally agree with her. I'm very, very impressed that something like a Loomis Wood diagram can come out of this. For me, if I look at the spectrum, it's just a wild forest of things. And then you all of a sudden see those band shapes in the Loomis Wood diagram. So I find this a very impressive analysis. Then we have Muriel Lepere from the Moore writing, very nice talk for great results. I really hope you have prospects to pursue this kind of measures. Associating a molecular jet and this configuration of IRsF1 is really promising for line positions. Yes, thanks, Muriel, for this comment. I also think there's good possibilities. Karen, if you now happen to have, I know we're still working on that part, but if you happen to have one of those spectrometers in your lab, what would be the next measurement you would like to do?
I have to unmute it so you can hear me say, Well, we're planning. I'd rather not talk about it right now, but we have some ideas.
Okay. Yet not to be made public. Julia Lehmann has a question. Is there any limit on the data point spacing here? It seems like these are really narrow peaks. Maybe Karen, can you go back to the slide where we see this
let's go back up
P1 and R0 lines?
Go back up a bit.
I guess yes, this one that's that's the wider lines in N2O, right? And then we have the narrow ones of CF4 somewhere where we kind of reach the limit of the step size. And yes, there is a limit to answer your question, Julia. That is kind of on the electronic side, there's no inherent limit, but on the electronic side, we of course have an analog to digital to analog converter with a finite resolution, and therefore the smallest step size that could be done in those measurements is 2 × 10⁻⁴ wave numbers, which is great to resolve lines of 1 × 10⁻³ wave numbers, and which gets to the limit of the called CF4 lines, which are only 6 × 10⁻⁴ wave numbers wide. Maybe I also have a question just about this graph here. We've seen the narrower lines of CF4 in the 6 × 10⁻⁴ range, and now here we're up to a few × 10⁻�3. Can you explain to me why we observe broader lines for the N2O measurement than we do in CF4?
Yes, that's the reason for this is that we had a pretty weak signal from that. I was talking a bit with Pitt about this earlier this week, and we had a weaker signal from the CHCl to F and N2O measurement than we did from CF4, and so we had to do it without the skimmer, and that means that we had a mixture of all the different temperatures, and so that makes it a little bit more difficult and not quite as easy to manage. So this would be the problem. I hope that fills in a bit.
Okay, I see. Yeah, that's why there are those wider lines. We have a bunch of new questions coming in the Q&A. Jean Clément asked, very nice talk. The results are really impressive. How much time did it take to realize the spectrum while combining a good spectral resolution and a good time resolution? Do you remember how long those measurements took, Karen?
No, I talked a bit with Pitt about it, and so it depends really on which of the ones he was measuring. But I'd ask him more about it and ask him how long it took precisely, because it does work out to be, the only thing I can do is I can compare it to the FTIR, and it works out to be significantly less. Yeah,
I think with the 2 × 10⁻⁴ step size, there is something like more than 1,000 steps to fill the gap of 0.3 wave numbers. I think something like 1,200 steps, and since each laser is stepped individually, there's 2 steps per step, so there's something like 2,400 measurements here. And now using the slow processor that was available 2 years ago, I think those measurements took a few hours, but I also couldn't give the exact number. But that also brings us back to the announcement that I made at the beginning of the talk. With the fast processor now, those measurements would get 20 times faster. So they should be down to some, well below an hour, certainly, to complete. Being 20 times faster probably means instead of 3 weeks of measurements, we would have completed it in 1 day. Julia asked, what is the sort of limit of detection with a single pass through the molecular beam? This question probably has many dimensions, and of course depends a lot on the substance that you use and the molecular beam that you use. But maybe answering it just in terms of the signal noise, I guess we can see it right here on the slide. So there is a signal noise on the order of 10 to the -3 absorbance units, and that is, do you remember the integration time for this measurement? That's probably 100 microseconds or a few hundred microsecond integration.
Right. I think I would guess at 100, but I think if this is the one I'm thinking of, this is spectrum I'm thinking of, it would be 100, because it was a 2 to 3 microsecond, I think.
Okay. Yeah, so of course the signal noise always depends on the integration time, but typically what we get is 10 to the -3 absorbance units on 100 microsecond time integration, and then you can estimate the limit of detection from your absorption strength. Patrick Dupre asks, can we have an idea of the sensitivity on N2O you show in 0.1% and the absorbance? Okay, I guess that question was closely related to what we just answered. Exactly, 0.1% absorbance is a typical noise level, but it really strongly depends on your time integration and your co-averaging. So the lowest noise levels that we have shown in time resolved measurements were in the 10 to the -6 absorbance units range, but that was like thousands of measurements co-averaged. So yeah, it depends a lot on your system. Bastien asks, thank you very much for this nice work and presentation. The presented spectra are very clean. What is the SNR you obtained? Okay, I guess we've had that. So many people are interested in the SNR. Julia Lehmann asks, are you working towards cavity enhancement? I'll hand over the question to you. Are you working on cavity enhancement?
At the moment, not, no.
What we have is multipath cell is one of IRsweep's products, and people did combine the Dualcomb with the multipath cell. Cavity enhancement is yet to be shown. Muriel Lepere asks, are you limited in your measurement by the SNR? If so, what is the limit? So I think the limit of the SNR we've discussed, but the first part of the question, Karen, was the SNR limiting for your analysis?
Not really, no. So it generally, we were able to pick out the transitions that we needed to pick out.
Okay.
So I'd say that it wasn't bad, no.
Okay, good. And then Patrick Dupre writes, what are the potential spectral ranges of the instrument? Maybe I can answer this question. Overall, QCL frequency combs can be produced in the range around 1,000 wave numbers, maybe be a bit below 1,000 wave numbers, up to 2,300, maybe 2,400 wave numbers. So most combs that we have on offer are so far in the range 1,000 to 1,800 wave numbers. But we are just coming out with lasers in the CO range, which is around 2,200 wave numbers, and we're constantly working on increasing the number of available frequency combs. But as a general limit, I would say it's around if you want to give the largest limit, I feel comfortable to say around 900 wave numbers to 2400 wave numbers. That's probably what the technology can do. Then there is a question from Martin Quack. No, it's a note from Martin Quack. We work on cavity enhancement, cavity ring down in other experiments already, and this could be extended to this experiment in the future in principle. Okay, so Martin Quack does have plans to use a cavity with the frequency comb, and I'm very much looking forward to seeing those results. I think there's currently no more questions coming in. Did you have something more you wanted to say, Karen?
No, thanks. That's fine. Thank you very much.
Great. Yes, I thank you very much. It was a pleasure having you for this webinar and seeing those great results. And yeah, I look forward to further working with you and your group. Okay, and then goodbye. Thanks for everyone for joining, and talk to you soon.